In this video, we consider a problem of great significance to the oil and gas industry. Namely, we are interested in designing a long pipeline which can sustain the required operational conditions. So, we are given basic parameters of the pipeline. The wall thickness of the pipe, T, the midsection diameter, D, specific weights for the steel and the fluid, and the maximum allowable tensile stress in the pipe. Our task is to determine the maximum allowable spacing between the supports. So, in designing this problem, I can think of a very long pipeline, maybe say 1,000 miles long, and my task obviously involves many supports. So to deal with this problem in a rational manner, I will first of all think that the weight of the pipeline is represented as a uniformly distributed load of intensity W, and then I will think that the pipeline is essentially infinite. Okay, let us see what are the consequences of this assumption. So if I look at the spans, I have infinitely many spans, and they're all the same because the pipe is infinite and there is no way to differentiate between the spans. And so what I can say is that because of this, I can think that each span deforms symmetrically, meaning that the bending angle in the middle of each span is equal to 0. So each span operates as a symmetric beam. Now I can push this idea a bit further and say, if I look at the lines going through the supports, they also could be viewed as symmetry lines, and therefore by the same token, the angle there also must be equal to 0 by symmetry. Well, because of these symmetry conditions at the supports, we can claim that the beam between two supports should be regarded as a fixed beam. Both the deflection and the angles are fixed, of length L, loaded by a uniformly distributed load of intensity W. So in effect, what happens is that if I look at a single span, the rest of the pipe, both on the left and on the right, create the conditions that make it equivalent to the wall. Now, the problem is certainly much more manageable now, and let us see what we can do about it. First, let me calculate what is W. W is the weight of the pipe per unit length. It has two contributions, from the steel and from the fluid. And W delta Vs is the area of the steel times the length, delta X. For the fluid, the area is pi d squared over 4. The length is delta X. If I put it together, I obtain this expression. So in this expression, I introduce this ratio, and I will call this ratio alpha. It is a dimensionless number, and it tells me what is the significance of the contribution of the fluid to the specific to the distributed load W versus the steel. right? And of course, I will carry around this formula. It makes my life a little bit easier because it shortens the notation. So now let us proceed to the analysis of the beam. So this beam is statically indeterminate, right? And there are multiple ways of making it statically determined. And here is one way. So I remove both angular constraints, both at A and B, and I exploit the fact that the beam is symmetric, so that the reaction moments m0 at both ends are the same. And now what I can claim is the following, that the angle induced by the distributed load plus the angle induced by the pair of moment, the angle either at A or B, must be equal to 0. Both of these cases are tabulated. And now I can claim the following, that theta A equal to theta B equal to WL cubed over 24 EI minus m0 L squared over 2I, and it must be equal to 0 because there is a wall. So this gives me the value for the moment. And it is, of course, WL squared over 12. Now, let's see what we can do further. So first I draw the shear force and bending moment diagrams for a simply supported beam under a uniformly distributed load. Very basic bending moment diagram. You could also get it from the table by differentiating twice the expression for the deflection line. Then I have even simpler shear force and bending moment diagrams. V is equal to 0 here, M is equal to a constant. And now I can put these guys together and I will obtain that the moment in the middle of the beam is equal to W L squared over 24, and at the end points it is minus W L squared over 12. Now let us do the stress analysis due to bending. So I use the standard equation, my over Iz. That's the value for m, that's for y, and that's the value for the moment of inertia about the z-axis. This expression takes advantage of the fact that d is much larger than t, or the pipe with a thin-walled vessel. And also I didn't use minus here and minus here. That would be proper. I just simply put positive values. The maximum tension in this case will be at negative minus d over 2, which means at the top of the pipe, not at the bottom. Now I can make this expression a bit more explicit by substituting the value of W to obtain this result for the maximum stress due to bending. The stress to the pressure is pretty simple. Standard equations for pressurized cylindrical vessel. And now I can combine the two. So the axial stress has two contributions, one due to the pressure and another due to bending. The bending does not contribute to the hoop stress, and so these are the expressions for the stresses. And now we have to choose L based on the fact that one of the stresses or both of the stresses must be less than allowed. So here I have to decide which stress to choose. And in principle, it could be either one. But in all practical situations, in every structural code that involves analysis of pipelines, this is the primary stress of concern, sigma A. That's how typically the numbers end up. And I will follow this trend, and I will equate sigma A to the allowable stress S. Here we are. And then I can solve this equation for L, and that's the answer I get. And in this equation, I want to remind you that alpha is a dimensionless parameter, easily expressed in terms of given pipeline parameters.